Axiom 6 is the subset selection axiom. It says that if S is a set and P is a property that each member of S may or may not possess, then there is a set T whose members are precisely the members of S which have property P. For example, if S is the set of all natural numbers and P is the property of being a prime number, then this axiom tells us that the set T of all prime numbers exists. The axiom is sometimes referred to as the axiom schema of subset selection because really it's not just one axiom, it's one axiom for each property P. Axiom 7 is the axiom of infinity. This tells us that infinite sets do exist. It says that there exists a set S such that the empty set is in S, and if the set A belongs to S, then S also contains the union of A and the set with one element, namely A. So we know that the empty set is in S. We can now apply the fact that you can form this union to see that the empty set union the set with one element, namely the empty set, is also in S. And of course that's just the set with one element, namely the empty set, in S. Don't confuse the empty set with the set having one element, that element being the empty set. So we know that there's in S two elements so far, the empty set and the set consisting of the empty set. And we then apply this union again, and lo and behold we find another element in S, and we can keep going like this in an unlimited fashion, and therefore this axiom says that the set S has an infinite number of elements. Axiom 8 is the replacement axiom, and basically what it says is that if S is any set and f is a function defined on S, then f of S is a set. Once again, we can see that this is referred to often as the axiom schema of replacement because it's really a number of axioms, one for each f. Axiom 9 is the regularity axiom. It says that if S is any non-empty set, then there exists a set A in S such that A intersect S is empty. The regularity axiom prevents Russell's paradox from occurring in this system. We shall now prove that fact. Axioms 1 to 9 form the Zermeol-Fraenkel axioms for set theory. This theorem says that under the ZF axioms, no set is a member of itself. If this is true, then Russell's paradox cannot occur under these axioms. So let's prove the theorem. Suppose it's not true. So let us suppose there is a set such that S is a member of itself. Define the set T to consist of just one element, namely S. And this is a set by the pairing axiom. But now let's apply the regularity axiom to T. And what does it tell us? It says that the set T must contain an element with trivial intersection with T. But T has only one element, namely S. And so S intersect T must be empty. But this is not possible. By our assumption, S contains itself. So at S has as a member S, and T clearly has a member S, so S intersect T is S, not the empty set. So we have a contradiction, so our supposition is false. This means that S is not a member of itself. So we have proved that under the ZF axioms, no set is a member of itself, and consequently the Russell paradox cannot occur. While the Zermeol-Fraenkel axioms are regarded as the starting point for set theory, there is another axiom that is often added. That axiom is the axiom of choice. It says for any set of non-empty sets, there exists a set which consists of exactly one member of each set in the original collection of sets. Some people present the axiom of choice as follows. Given a set S of non-empty sets, one can choose one member of each set in S. So what we're saying effectively is that one can make an infinite number of arbitrary choices. Perhaps I should mention that we can also express the axiom of choice in a way that's a little closer to the sort of things we normally meet in topology. Basically, it says any product of sets, more precisely non-empty sets, is non-empty. This axiom of choice is not implied by the Zermeol-Fraenkel axioms, and for many years was highly controversial. Today we generally begin set theory with what we call ZFC axioms, that is, the Zermeol-Fraenkel axioms together with the axiom of choice. While it is common to begin with ZFC, many mathematicians still make clear if and when they are using the axiom of choice. The so-called constructivist mathematicians avoid using the axiom of choice. We discussed the controversial axiom of choice in Appendix 6 and mention that it is equivalent to Zorn's lemma and to the well-ordering theorem. Of greatest interest to us as topologists is that the axiom of choice is equivalent to Tikhonov's theorem, which says that any product of compact sets is compact. Finally, we mention the status of Cantor's continuum hypothesis, which suggests that there is no uncountable set of cardinality less than that of the set of all real numbers. In 1940, Kurt Gödel proved that the continuum hypothesis cannot be disproved using ZFC. In 1963, Paul Cohen proved that the continuum hypothesis cannot be proved using ZFC, and so the continuum hypothesis, often just written as CH, is independent of ZFC. But both of these results assume that the Zermeol-Fraenkel axioms themselves do not contain a contradiction. And while we assume that this is the case, it has not been proved. On that note, I should end the video. However, this has been a long and hard video, and maybe you deserve a small reward if you have continued to this point. So let me tell you an amusing story. To understand the story, you have to realize that many years ago, when I was first lecturing, there was no online material. You either went to a lecture or you missed the material that was in that lecture. So I recall that I was lecturing a topology course. And in the first lecture, there was a good turnout of students, and in the second lecture I noticed that one particular student was missing, and that student did not appear again during the entire semester, not even at the tutorials or problem working sessions. So it was a great surprise to me that in fact he did turn up for the exam. And when I marked the papers, this student got 98%. I was truly shocked. I asked for the student to come and see me, which he did. And he sat down and I said, "Look, I know that you came to the first lecture and you never came again, but you ended up with 98% in the exam. How is this possible?" He looked me in the eye and said, "Well, I would have got 100%, but something you said in that first lecture confused me." Thank you. Bye.